a process node that took Intel the better part of a development decade, 4 years of active rework cycles after its first attempt at 10 nanometers stumbled, plus billions in capital burned before a single working chip reached a customer, was reportedly matched in density on one critical layer by a Shanghai fab, using nothing but machines it could legally purchase. Not the machine every other competitor in this contest considers indispensable, the machines it was allowed to keep. That wafer, pressed from silicon in a fab that was supposed to be locked out of this competition, now sits inside a finished product somewhere. The race stake is this: Intel's lead has always lived in the calendar, in the years between nodes, not in the size of any single node. The question running through every split in this video is whether that calendar gap is still wide enough to matter, or whether it is being consumed faster than Intel can add the next page. A breakthrough is not a scoreboard flip. It is a change in the rate at which the gap is being consumed. The story here is not who has the better chip today. It is whose node clock is ticking faster, and whether Intel can lengthen its stride before a challenger without the critical machine closes the same ground. Picture a wafer. 300 millimeters across, origin at a fab in Shanghai, surface polished to within a few atoms of flat. Intel's 10-year head start is physically written into the geometry of that wafer, in how tightly the circuit lines are drawn, in how many good chips come off it, in how many times light has to cross it to print a single layer. That wafer is the object this race is actually about. Follow it through every leg. The first leg is density. How tightly can you draw the lines? Intel's approach to node progression ties each jump to an institutional project. The move from 10 nanometer to 7 nanometer class, internally branded Intel 4, later Intel 3, consumed years of active development even after Intel had already spent a development cycle reworking its earlier 10 nanometer attempt. The design rules that define a node, the minimum metal pitch, the contacted gate pitch, are not engineering choices an individual team makes in a sprint. They are the product of thousands of engineer years baked into process chemistry, into the behavior of light at specific wavelengths, into the statistical tolerance of hundreds of sequential steps. Intel's public roadmap has historically projected node jumps in 2 to 4 year windows, and that is after first silicon already exists. Getting to first silicon is the R&D phase before the ramp. Reports from technical outlets tracking Chinese semiconductor output claim that SMIC achieved 7 nanometer class density on at least one critical layer of a finished product, using a technique called self-aligned quadruple patterning on deep ultraviolet machines it already held. The company's own disclosures on process specifics are sparse. Independent wafer-level benchmarking has not been publicly confirmed. The claim, as reported, involves a contacted poly pitch in the range Western analysts associate with a 7 nanometer class process. Treat this as reported and company adjacent, not independently verified. But the product ships. The density on that one layer is not entirely fabricated. Think of design density like writing on a postcard. Intel spent years developing a pen thin enough to fit a novel on one card. SMIC reportedly got to similar letter size by writing each line 4 times in slightly offset passes, layering the strokes until the effective line is just as thin. More passes, same card, different physics. The pen Intel uses makes 1 stroke. SMIC uses 4, calibrated against each other with precision that most Western process engineers said was at or beyond the practical limit for deep ultraviolet light. Here is my read on this, and it differs from most Western analysts. The 7 nanometer class story is being dismissed as a parlor trick, a single-layer benchmark that does not generalize. I think that framing misses the more important signal. The trick is not the achievement, it is the proof that SMIC internalized a workaround methodology faster than the export control architects assumed was possible. That methodology compounds. A team that figured out quadruple patterning faster than projected does not stop at the problem they just solved. They apply the same learning acceleration to the next constraint. That is the rate change that matters, not the node name on the press release. Intel's pace to cover one node generation, roughly 2 to 4 years of active development per jump, based on its public roadmap history. SMIC's reported pace to reach comparable density on one critical layer, within a single product cycle of the export controls that were supposed to stop it. Reports suggest under 2 years from restriction to demonstrated node, from a half-decade to a product cycle. That is the first compression. The wafer that just proved SMIC can draw tight lines now has to prove it can be reproduced 1,000,000 times without falling apart. That is where the second clock starts. And this is where I think the optimistic China narrative breaks hardest. Not because Chinese engineers cannot solve yield, but because the multi-patterning route makes yield a fundamentally harder problem than it is for extreme ultraviolet fabs. More passes means more chances for a misalignment to kill a die. I am testing that hypothesis through this leg and the break that follows. The second leg is yield. How many good dies actually come off that wafer? Intel's mature nodes run at yield rates that reflect decades of process maturity and tight statistical control. Getting from first silicon to volume yield is an 18 to 36 month ramp, even with proven equipment and a process that has already been characterized. Intel and TSMC's published timelines for ramping a new process to high-volume manufacturing consistently land in that range. And that is with tools optimized for the process, with yield engineers who have run thousands of wafer starts on similar chemistry, with a statistical baseline built from years of production data. SMIC's yield on its reported 7 nanometer class process has not been independently benchmarked. Analyst estimates vary. Reports from firms tracking Chinese fab output suggest SMIC is producing meaningful quantities, enough to put chips into finished products. But the cost per good die is a persistent open question. The multi-patterning approach multiplies the number of process steps, and each additional step introduces another statistical chance of a misalignment that kills a die. The yield ramp on a multi-patterning process is, by process physics, harder than on a single exposure extreme ultraviolet process. This is not a policy fact. It is a consequence of how errors accumulate across sequential exposures. Think of yield as the attrition metric of the race. Imagine a relay where you drop the baton on a random exchange. Single patterning runs 4 exchanges per layer. Quadruple patterning runs 16. The team that controls every exchange to the same standard wins. The team that adds exchanges without proportional control, improvement drops more batons per race. SMIC added exchanges. The question is whether they controlled them. Picture the wafer as a vinyl record. Every scratch across that record is a dead die. Single patterning makes 4 passes with a needle per critical layer. Multi-patterning makes 16. The record that went through 16 passes has more scratches, statistically unavoidably. Scale that to a production run of 1,000,000 records, and the number of playable albums leaving the factory is what determines who can actually compete on price. A 300mm wafer holds hundreds of dies at advanced nodes. If yield is, say, 60% versus 90%, and these are illustrative numbers, not reported figures, the difference in good dies per wafer is dozens of chips per run. Multiply across millions of wafer starts per year, and the economics of who can sell at competitive prices begins to separate sharply from who can demonstrate a node on a single test wafer. Intel's time to ramp a new node to volume yield, consistently described in public roadmap documents as a multi-year industrialization program after first silicon. SMIC's time to volume yield on its deep ultraviolet multi-patterning process. No independent figure is available. Analysts describe it as still ramping, with yield economics characterized qualitatively as a work in progress. The split here is not a number. It is a posture. Intel's yield clock runs on a known curve, built from institutional memory and process data accumulated over decades. SMIC's yield clock is still being set. The gap on yield is not compressing. It may be widening as SMIC pushes into territory where multi-patterning's error accumulation is most punishing. The wafer can be drawn tight. Whether it can be drawn tight 1,000,000 times at a cost that makes business sense is still open. But here is what makes this race genuinely strange. SMIC is running this entire sprint without the machine that every other competitor at this node range considers the price of entry. The third leg is tooling, running the race in the wrong shoes. Extreme ultraviolet lithography machines, built almost exclusively by ASML in the Netherlands, print a single layer of a chip with one pass of light at a wavelength of 13.5 nanometers. A single extreme ultraviolet exposure can define a feature that would require 4 or more deep ultraviolet exposures to replicate at comparable resolution. At leading nodes, extreme ultraviolet is not a convenience. It is the economics of the entire process. Each extreme ultraviolet machine costs upward of $150 million and requires a supply chain of components running through Germany, Japan, the United States, and the Netherlands. ASML has been prohibited from exporting extreme ultraviolet machines to China under successive rounds of export controls. Intel, TSMC, and Samsung all use extreme ultraviolet lithography at their leading nodes. SMIC cannot buy one. SMIC's reported workaround is the self-aligned multi-patterning approach using the deep ultraviolet machines it legally holds. Tools that are older, cheaper, and theoretically incapable of the resolution extreme ultraviolet achieves in one pass. The multi-patterning technique uses multiple exposures with precise offsets and etch steps to shrink the effective feature size below what a single deep ultraviolet pass can achieve. The technique is not new. TSMC used it at earlier nodes, but pushing it to 7 nanometer class geometry with deep ultraviolet machines is at or beyond what most Western process engineers projected as the practical limit. SMIC is also reportedly developing domestic lithography through its state-backed tool building program, but outside analysts assess the most advanced publicly demonstrated domestic tool as several generations behind current leading-edge deep ultraviolet. Extreme ultraviolet versus deep ultraviolet multi-patterning is the difference between drawing a straight line with a ruler in one stroke and drawing the same line by laying 4 pencil strokes at calibrated angles and erasing between them. The ruler is faster, cheaper per line, and more accurate. The pencil method can get you to the same line. It takes 4 times as long, and every stroke that lands even slightly off wrecks the entire line. SMIC is the pencil team. The question is not whether they can draw the line. They have. The question is whether they can draw it 4 million times before the ruler team draws it 5 million. Extreme ultraviolet throughput at a leading Western fab, 1 pass per layer, with a machine throughput measured in wafers per hour on current generation tools. SMIC's deep ultraviolet multi-patterning equivalent for the same critical layer. Reports suggest 4 or more passes per layer, each requiring precise alignment and intermediate etch steps. Analyst estimates put the cost per wafer premium for deep ultraviolet multi-patterning at advanced nodes as significant, some describing it as multiples of the extreme ultraviolet equivalent. The gap on tooling cost and throughput is not compressing. SMIC is absorbing a structural tax on every wafer it runs at this node, and the machine that would remove that tax is sitting in a warehouse it cannot reach. 3 legs. The density gap compressed, the yield gap held. The tooling gap is a structural cost premium that does not move. That is the honest break, and it is the most important split in the race. The gap that is not closing is sub 5 nanometer at volume. The gap that is not closing is cost per good, die at production scale. The gap that is not closing is yield economics on a process that multiplies every error source by a factor of 4 or more. The strongest version of the argument that SMIC's progress is real and durable, the wafer exists, the chip ships. The density on that one layer is not fabricated. Reports from credible technical analysts suggest SMIC achieved something in the 7 nanometer class range on at least one product layer, under conditions the export control architect said would make it impossible. If the density gap closed on one layer without extreme ultraviolet, the argument goes, it is a matter of time and iteration before it closes on all layers. Domestic extreme ultraviolet is coming, slowly, but not never. Chinese fab investment is accelerating, not decelerating. The institutional learning curve is real, and SMIC proved it bends faster than projected. The strongest version of the argument that Intel's lead is real and structurally durable Sub 5 nanometer at volume is a completely different contest from 7 nanometer class on a demo layer. Intel's Intel 4 and Intel 3 nodes are in high volume production at yield rates and cost structures no Chinese fab has publicly approached. More critically, SMIC's multi-patterning route hits a physical ceiling that deep ultraviolet cannot exceed regardless of engineering ingenuity. At some feature size, the wavelength of the light itself becomes the limit. Extreme ultraviolet's shorter wavelength is not a policy advantage. It is a physics advantage. Without it, SMIC cannot reach the frontier node. It can only approach the previous frontier. And Intel, TSMC, and Samsung are not standing at the previous frontier. They are 2 nodes past it, running extreme ultraviolet at high volume, and already developing high numerical aperture, extreme ultraviolet for the node after that. My synthesis is this: both reads are right on different time horizons. The gap at the demo wafer level is closing faster than Intel's roadmap assumed. And that pace matters because it changes the rate calculation going forward. But the specific gap that defines commercial leadership at the frontier, cost per good, die at sub 5 nanometer volume, is not closing. The physics of the tooling barrier makes it structurally resistant to the same workaround methodology that worked at 7 nanometers. SMIC proved the methodology scales further than expected. It has not proved the methodology is unbounded. Both things are true simultaneously, and the geopolitical question is, which gap the market actually prices. 12 months from now, SMIC will likely demonstrate continued progress at its current node, possibly with yield improvements that bring cost per die closer to viable for domestic applications. Intel's Intel 3 and its most advanced nodes will be in or approaching volume production, maintaining a lead of at least 2 to 3 node generations at the frontier. The density gap at the demo wafer level narrower than 2 years ago. The cost per die gap at volume roughly stable, possibly wider. The tooling gap unchanged unless a domestic extreme ultraviolet breakthrough is announced, and no credible technical report suggests that is 12 months away. My plain call, SMIC has changed Intel's threat model in a way the export control architects did not price in. Not because SMIC is catching the frontier, but because SMIC proved the workaround methodology is more generative than anyone projected. That changes the pace calculation. Intel's lead is real and probably durable at sub 5 nanometer for this cycle. But the rate at which the gap closed at 7 nanometers suggests Intel cannot assume the next node jump buys the same number of years it used to. The calendar is getting shorter. That is the threat, not the scoreboard today. That wafer we traced from Shanghai came off a machine that was supposed to be incapable of printing what it printed. It shipped in a product. It is sitting in a device somewhere. The fact that it exists changes what the next wafer has to do, and what Intel has to do to stay ahead of it. A breakthrough is a new rate, not a new rank. SMIC did not overtake Intel. It changed how fast the distance between them is being consumed, and that new rate is what Intel has to answer, not the chip that proved it. The machines that were supposed to keep this gap open are still sitting in Dutch warehouses, and the gap is still closing. Here's the question I want you to sit with. If SMIC can reach 7 nanometer class without extreme ultraviolet, what node does it reach when domestic extreme ultraviolet finally ships? And in what year does that wafer become the one Intel actually has to race? Drop your call in the comments. And if this kind of split-by-split breakdown is how you want to track this race, subscribe and turn on notifications, because the next node cycle starts sooner than the roadmap says.